I would recommend JIT only if you absolutely have to use it. You have to use it if you do not know your target platform. The other reason would be that you're running programmer language that is very hard to ahead of time compile because it's so dynamic.
Then I want to change topics a tiny bit and get into the 1 billion row challenge.
I thought my solution is perfect. It can never get better. But then about 6 hours before the deadline is like some other person was like submitting a new solution and was overtaking. It's always best to, at least initially, go for a simple solution, even if you know it's not the optimal one. I learned this also when I was training and measuring my timings for the programming competitions.
Hi folks, and welcome to a new episode of The Marco Show. Today we're going to be talking about GraalVM and my favorite topic as of late, the 1 billion row challenge. And I think I have the perfect guest with me today to walk us through these landscapes, so to speak. Hi, welcome, and who are you?
Hi Marco. I'm Thomas. I'm the GraalVM founder and project lead. I'm a vice president at Oracle, and I'm currently leading the GraalVM team, and I'm very passionate about compilers and programming languages.
Right.
Which is why I thought I'm at the perfect place here at the JetBrains office in Munich. And
yes.
Thanks for inviting me here.
Yeah, thank you for being here. We love to have you here. Then to jump in, for people who might not, even though it might be impossible, but for people who might not yet know what GraalVM is, could you kind of sum up, give us a short 30-second version of, first of all, what it is? And then I'll dig a bit deeper into it.
Yeah, so GraalVM at its core is a runtime for many different languages. So we can run JVM-based languages, we can run Python, we can run JavaScript. And our aim with GraalVM was always like, yeah, let's make languages run more efficiently, and meaning more faster, with less memory, and let's make programmers more productive. And so the project has a pretty wide angle. And therefore, it's a little bit difficult to pin it down to just one thing, because we operate in many different language ecosystems, and we have different artifacts that we ship to users. But at the core of it, it's like run programs faster and make programmers more productive.
It's interesting because when I talk with people at conferences, for example, or other people, I have the impression that GraalVM almost always kind of means for them the native image, abilities. And then I had a look online at the documentation, and then we have the Graal compiler, we have native image, you have Truffle language implementation framework, you just talked about polyglot API. What does all of that mean, so to speak?
Yeah, I mean, native image is one of the most popular features of GraalVM because it gives a new ability to run JVM-based languages in a very, very efficient manner, meaning with a super low startup and low memory footprint. So it opened a whole new world for developers of JVM-based languages. But the other things like Truffle is more a code word for our multi-language story. Mm-hmm. Because at GraalVM we didn't want to stay in one language ecosystem. We always thought that it's actually a big waste of engineering resources that the different language ecosystems are replicating the same components for every language. Mm. Like if you look at, let's say, the way JavaScript is run in the browser, the way Java is run on a JVM, the way a Go program runs, each of them has their own garbage collector, has their own compiler, has their own runtime system. And the core research idea behind the GraalVM project that we started now it's almost 15 years ago, was that why can't we just develop some of these very complex runtime components like the garbage collector, compiler, runtime system? Why can't we program them just once and then reuse them for the different languages? Mm-hmm. And so this is at the core of what we call the Truffle framework, that it provides this ability for a generic runtime system, meaning that consists of the Graal JIT compiler and the garbage collectors of Graal, to serve many different languages. Mm-hmm. And we are serving popular languages, like we have a Python implementation, we have a JavaScript implementation, but there is also other people even building their own language implementation or their very domain-specific language on top of that framework. The most notable among them is the Pickle language from Apple, which is a build script language that is becoming more and more popular. It is built, for example, on top of the same language implementation framework as all of our other languages. And this kind of architecture of the Graal project as a whole, with languages on top and then a language agnostic language implementation framework, and then underneath the complex components like our JIT compiler, our runtime system, and so on, this allowed the project to scale well beyond just a single language. Mm-hmm. And this allowed us to really scale up and to reuse the engineering efforts we put on the lower levels of the platform.
I'd actually want to get into that a tiny bit later. Just to pick up a point you just mentioned, you said you're a founder of GraalVM, and 15 years it has been around now. So how did it all start? Where did the original idea come from? Was it just you sitting at home and then thinking, hey, that's what I should be doing? How did that come about?
No, absolutely not. It was actually even before 15 years, the original ideas around GraalVM already were explored as part of Sun Microsystems Laboratories. So Sun Microsystems Laboratories is, by the way, the research organization that I think it's now 30 years ago was starting with Java research or creating the Java language. And in this kind of research organization, we had a research project that was called the Maxine VM. The idea was to write a metacircular VM for Java, so a Java virtual machine that's also written in Java. And in the context of that project, I was an intern when I was a student. And I was a very ambitious intern, and we were developing compiler technologies there. And so this is where some of the original code that's now in the Graal JIT compiler was already developed. But back in the days, it was just one language. It was just a Java VM for Java. And but then there was some uncertainty because of the Sun acquisition of Oracle. So I decided my next internship should be not at Sun anymore, but I would go to Google, which is why I ended up in Google in Denmark at the V8 team. And I was developing the crankshaft JIT compiler at the V8 team. And so there I was actually switching from writing a Java VM in Java to writing a JavaScript VM in C++. And it was a very good experience for me. It was very, very nice and very interesting. And part of that experience for me also was like, hey, I mean, those two VMs, we're actually developing very similar things. It's not as different as you would think. And from that, when I later joined then Oracle Labs, so the Sun acquisition was completed and Sun Labs was now Oracle Labs. And when I joined Oracle Labs, it was always then part of my core research ideas was always, okay, I was before developing a Java VM in Java, I was developing a JavaScript VM in C++. Why can't we combine those things and reuse here the one runtime system, the one JIT compiler for multiple languages? So this is why this core idea was always there. Now we had also this problem, so to speak. How do we sell this core idea to management? Because well, you're at a research organization there, and you're supposed to research a certain area. But how do you now convince management that we should not only write a Java VM, we should also write a JavaScript VM at the same time, right? And because initially, management came to us and said JavaScript VMs, there's no money in JavaScript VMs. Like, why you developing this? But you were lucky because we had this research collaborations with universities, and we had there a very ambitious master student, Andreas Wöss. He was ambitious, and we had that master student then develop the JavaScript parts. So we ourselves didn't have to do that. But it was a case where we had a lot of constraints here because I only had one master student part-time for one semester, and I needed to come up with a JavaScript implementation that is a prototype reasonable enough to showcase the power of the concept, right? And because at first we were thinking of approaches of converting JavaScript IR to our compiler IR, and we even started doing that, but it was just too complex. And this is when we were like forced to actually think of a solution that would allow a relatively junior master student to develop this in a very short period of time. And this key constraint we had actually allowed us and forced us into inventing what we now call the Truffle language implementation system, which is a system that allows you to develop languages by only writing an interpreter. So the way it runs is you write an interpreter in a certain language, and that's all you have to do. And the rest is automatically done for you. And the most important part of this aspect is that the JIT compiler is automatically derived from your interpreter definition. Mm-hmm. So you define the interpreter defines the semantics of your programming language, and the JIT compiler is parsing what you wrote in your interpreter, and in this way recognizing the semantics automatically. We call it partial evaluation. This is the term, the academic term for this, but this was the core aspect of how we could get to multilingual support without complex additional components.
What kind of kept you going with all of this? So, this is kind of a personal question, I suppose, but even when you said you were an ambitious intern back in the day, what made you so interested in this entire topic? And maybe if people want to follow your footsteps along, you just casually mentioned that I worked on V8 at Google. How did that come about, kind of?
Yeah, I was always interested in compiler and language technology as a meta technology, right. as you program, like how the compiler would make your programs faster. Right. So it was something that interested me very early, right? Now, and it was always for me also an ambition to, and this is why I did internships at multiple companies. I would actually also recommend this to young people to try that, because this way you can really then explore multiple teams and capture the mind share of multiple teams. And that's why for me, this experience of interning at Sun Microsystems back in the days, then at Google and so on, it was very very important, I think, for me early on to get this like comprehensive view of this field. And then once you start going into a certain direction, right? At some point you become invested. so as you know, and the GraalVM project, right? It was still a research project with only a couple people and no users, right? No, we always joking, no users, no problems. Because you don't get bug reports. You just develop on your own, right? But back in the days, we're like a small team, because if you have a research project, you can only have a couple people, and they will fund you based on a belief that this will eventually be interesting, right? Mm-hmm. But over time, as we grew more and more successful with the project, and it started to get users and so on, right? Then suddenly the project was growing, and then you have all the other aspects.
How did that work, by the way? How did the project suddenly grow? How did you go from that, let's say, research phase to, hey, suddenly there are a bunch of users and more are coming? What happened there?
So we were actually operating in a research mode for a very, very long time between 2011 and 2018. Only in 2018 was when we did our open source release of our software. To a broader user base. Mm-hmm. We had internal users before then, internal users at Oracle, but in terms of external users trying our software at a large scale, it was only in 2018 when we did the open source release of our software. And that was a very exciting time because it was the first time we could show the software that we built to really a large audience and had many, many eyes look at it. And our strategy there was that, our strategy always was based on we built some awesome technology here, but we are not really the experts in understanding how this technology should be actually applied in the real world. Mm-hmm. And so when we pushed this open source release, we intentionally made it relatively broad, and we made like a blog post that said top 10 things to do with GraalVM.
Right.
Because you're like, let's just.
Did you just come up with these top 10 things?
Yeah, it was just brainstorming. Let's just fantasize. I mean, nowadays you would ask some AI bot,
Right.
imagine 10 things with that technology, right? But in this case, we used the common intelligence of the whole language community and the world, which is actually a lot better, even. And so there we came up with these 10 things. Just some of them sounded a little crazy, but that didn't matter to us, right? And the goal here was really let's throw these 10 things on the wall and let's see what sticks, right? And this was then very valuable to us that over the next 6 to 12 months, suddenly we saw which part of these 10 things that we were suggesting actually got a lot of positive feedback, and which ones were like, didn't get any
What was the main thing back then which sucked?
So the main thing that was actually surprising to get this more positive feedback than we thought was native image. Mm-hmm. Because when we developed native image, so native image is a ahead of time compilation for JVM-based languages, and we never intended native image to be such a big part of this whole project. We always thought, the polyglot aspect is the, because we found this just a little more exciting than the other parts from a research perspective. And it was for us, native image was for us developed primarily because in order to grow our project internally at Oracle and to get more funding, we were developing something that attached our product to the main and most important, software at Oracle, which is the Oracle database. Exactly.
Oh, right. Okay.
So the Oracle database, which is a really awesome technology, is the Oracle database team was interested in executing other languages in the context of the database. The idea there is you have the data all there, and now you want to run your programs that operate on the data directly there. Because why would you kind of pull out all the data in the database in some expensive memory, and then that already costs you over the network and so on, and then you run it there. So all of this is very expensive, and instead you could just run the program on the data where it is. That's right. And then in general, now also our current research is going a lot into this kind of directions.
By the way, does that mean you sort of had the Oracle database team as your stakeholders? How do I have to imagine that in terms of the funding being approved, that you had to make them or other parts of the company happy, or how does that work?
Yes, I mean, the Oracle database team needed to say that they were interested in this line of research, and that if it would come to fruition, they would be willing to ship something on top of that, right? And for us at Labs, it was always about technology transfer. In the sense, you build your project, you build your research, but at some point you want to transfer your research to a product. Mm-hmm. And for this, a lot of the ideas, once you wanted an idea to be funded, at a larger scale, you needed a product group sponsor, right? You need somebody with, a real product and real revenue and real money, right? to say, yes, I'm interested in that, and I would be willing to sponsor it, and I would be willing to, if the research here is successful, I would be willing to ship it as a feature in my product. Right? Mm-hmm. And the Oracle database team was interested in that, and so, but now we had the problem that we had this runtime system built up and written in all of our technology is written in Java. Like our JIT compiler is written in Java, our garbage collector is even written in Java. And so we have this Java-based technology, but we want to embed it into a C++ or in C, a technology written in C. And more importantly, I want to embed it into a technology that itself thinks it's an operating system.
Okay.
because if the Oracle database, when it's running on a certain computer, right, it wants to control everything like an operating system. It does its own scheduling, its own memory management, and it has its own like virtual operating system layer that can where it runs on top of. And so it wants to control a lot of the low-level details of how things are working. And this is why it's very hard to, let's say, embed something as complex as the Java hotspot virtual machine into that database, because the Java hotspot virtual machine also wants to be operating system,
right?
Also wants to control everything.
Right.
So we need to come up with something more lightweight and embeddable. And for this, we thought, okay, why don't we pre-compile our Java code into machine code up front? So we don't need a complex, JIT compiler and other runtime system components anymore. And so this is why we developed this ahead of time compile feature for this embedding use case. But this also meant we developed this feature only for us.
Right.
Because we are like, oh, nobody else is going to use this. Only we are going to use this. And we use this property for simplifying our development, meaning we cut all sorts of corners because we were like, okay, we are not using these and these complex features, so we don't need to support them in our ahead of time compilation, right? Because it's only for us. But then when we published this open source project in 2018, suddenly people were like, oh, this ahead of time compilation, it has like this really good properties. I want to use it for my application server. I want to use it for my microservice, right? And then suddenly users started to use this relatively like narrowly designed tool for much more complex use cases than we thought. And this is why then after we went open source with it later, we had to accommodate and improve this feature a lot.
What does then happen to a project like Graal in terms of, I guess, so you're, let's call it academically, obviously your research project, you have your in-house stakeholders who have certain expectations, suddenly you put it online and you have a ton of outside world expectations. Isn't there sort of a lot of tension of where the project then is supposed to go and what is supposed to happen next? And does that take away from your research freedom, so to speak?
Yes, I think it does. And I think you're absolutely right. Once you start publishing your project in a way that you have a lot of other stakeholders, internal or external, and once you have a lot of users who have their own opinions and so on, right? This is where you really like transition away from a research project, and then you become yourself almost a product, right? I mean, I said before that the point of labs was always to kind of transfer technology into an existing product, right? With Graal, it was more like actually the Graal itself then, after this open source release and having all these uses, the Graal project itself transformed from a research project into a product, right? And also 1 year after the open source release, we were on an actual product that you could buy support from. But this whole research to product, it was always a bit of it's kind of like boiling a frog, it's like it slowly gets, the water gets more and more producty, right?
Right.
And that's also, I mean, it's true that also for the team and so on, right? It's as you the way you work, right? It becomes different. When you were a small team, you were moving very quickly and you were like, exploring ideas very aggressively, right? and suddenly, you have a bunch of things to maintain, and you need, different platforms to support, and you need to fix the bugs. Before you didn't have bugs because it's only your research paper.
Also for yourself, did you morph into some sort of PM then? I mean, early on, obviously writing all the stuff yourself, but then, did your role yourself change?
Yes. My role changed a lot. Yeah. So I was in the first couple of years on the project. I was individual contributor, and I was programming large parts of the system. But then, as the project matured and the team was growing, I was myself forced to go from engineering to management. And yes, it was a transformation also for my job role, right? It was, and I definitely would enjoy engineering more. because engineering is just it gives you a better sense of accomplishment. I feel like once you program something and it runs, and you really feel like. Whereas once you start to go into management, your accomplishments and your become less clear because, well, what did I do today other than 5 meetings? So that's definitely the case. That if I had a choice, I would rather continue with engineering. But on the other hand, I kind of felt I had to go towards management because I wanted to steer the project and as it grows larger, still have the ability to make sure the project goes in the right direction as a whole. And a project this large can only scale if you start building a full organization.
And so from 2018, when you said open source and then the initial wave of demand, so to speak, what happened then over the next 7 years, I guess? What was the direction you said then for that new organization to be built? What should you focus on?
The directions we were following was primarily then based on the feedback from users and then customers, and we felt, of course, that we needed now to be a little bit more focused, let's say, because we have these top 10 things, 10 crazy things to do, but actually only, 5 of them were of interest to some people. And from those 5, you have 2 that are very clear, right? So that's why we started actually focusing, of course, the project a lot more on these things where we got so much positive feedback from. Mm-hmm. And one of them was native image and this ahead of time compilation, which we felt was getting the best response from the community. Because suddenly you could take a Micronaut application and then it starts the server in 5 milliseconds. Yeah. And that was very exciting at the time and still is. But nowadays people take it for granted with native. Yeah. But it opened something for Java microservices that was just not there before, right? And that's why we focused a lot on ahead of time compilation. And then the interesting was then, I think, less than 1 year after we went out, Red Hat was publishing the Quarkus framework, and they didn't tell us about it before. But I open Hacker News and I go to the announcement of Red Hat's Quarkus framework, and I see, this is completely built on GraalVM native image as a core value proposition of Quarkus, right? That was very, very surprising for us because we were not in coordination before, but we were also very happy because suddenly they could actually, with their framework, even further showcase the benefits of that. And but then we started working with even more members of the community, also the Spring team, to make sure that Spring has support for native image and this ahead of time compilation. And so this is the area where I think we focused a lot, right? And in the multi-language space, we are still doing multi-language, but we are also currently focusing down on a slightly fewer languages because we did underestimate a little bit how complex it is to implement some languages. Right. Because and the problem here is not so much the language itself. Because the language is, you can you can emulate relatively quickly. But the problem is that various languages have not very well-defined native interfaces. So with Java, we are like in a situation where there is the GNI specification, the Java native interface specification. And so it's very clear how a native extension is built. But with Ruby, for example, or also with Python, such a thing doesn't exist. Meaning everybody who builds a native extension in Python is just importing the header files of the Python interpreter. And that contains so many methods that we will have to emulate and so on. So in general, our language implementations in these areas, they're very complex to build. They need relatively large teams to be compatible. And this is why we are currently focusing our effort on the most popular languages only.
Interesting. Just to get a tiny bit back on the Java ecosystem, so to say, you mentioned then you work with the Spring team and then you had other teams. Did you ever feel any pushback for the ideas, by the way, also? I mean, at the same time of native image? And how did that go?
Yeah, sure, absolutely. I mean, every idea that becomes popular gets a lot of. The more popular it becomes, the more sometimes people are pushing that harder. One of the main criticisms of native image has always been that it is requiring restrictions and configuration for your applications to work with the native image. Now, part of this was specifically early on. We had more restrictions because, as I said, native image was developed just for us. So you're willing to take a lot of restrictions to get to the goal faster. But I think over time, we worked a lot on native image to make it more accessible. And specifically, once we started working with the frameworks, like with Spring and Quarkus, they gave us very good feedback on what would be necessary to make this practical. And then the complexity of developing a native image is hidden in the frameworks. And this is why nowadays we are still saying that if you want to use native image, you should use one of the major 3 frameworks, which is Spring, Quarkus, or Micronaut. And if you use one of those frameworks in its latest version, then the experience should be relatively smooth.
And then you'll always have someone who uses some sort of incompatible library who will probably complain at some point. But overall, I guess it's now a relatively smooth process.
Yes, it's a relatively smooth process. And we also started to be a little bit more relaxed about the configuration by allowing more wildcards. So if you, for example, say I have this one library here and I really don't want to configure now every method in it, you can nowadays in the latest version of GraalVM, you can just specify a package, and then everything in the package is included in the image. Because the fact that we were restricting here reflection is primarily to make sure the image is smaller and runs more efficiently. But it means that if you have some parts of your app where you don't need that restriction, you can nowadays actually use a wildcard for that. And that makes it a lot smoother. And we are developing further in this direction with, nowadays we even support dynamic class loading in our our early access builds, because we can even load a class at runtime and dynamically interpret it if necessary. Now, all of this, of course, is starting to be a trade-off again because it takes away a little bit from the benefits of actually going full ahead of time compilation. I mean, the most obvious benefits to people was the startup. That's the thing that's, of course, in nowadays social media-driven world was like giving us the most viral content because you have a Java app and suddenly it starts in 5 milliseconds. Okay, so a full Java server with Micronaut. And so that's the number one benefit, but and that's why a native image is used a lot in serverless environments, for example, where this fast startup is something you absolutely want, right? Now, the second benefit of it from an execution perspective is that it uses a lower memory footprint, and that is because all this metadata you need to later, like just-in-time compile at runtime, it takes up a lot of memory, and also the just-in-time compilation takes a lot of memory. So if and in a cloud environment, right, you don't see that so much when you run on your local machine, because your local machine might have 16 cores and 15 of them are idle like 90% of the time, right? So there this cost is hidden.
Right.
But in a cloud environment where typically the machines are saturated, maybe even overbooked, and so they're like spending extra CPU resources then at runtime in your high availability machine is very expensive and very like it's not very clever to do that there, right? And so this is why the lower memory footprint was another aspect of the of the benefits here, right? And on peak performance, of course, there was at first like one of the first counterpoints to native image was like, yeah, maybe you start up fast, but you don't run at the good peak performance later, right? Because the JIT compiler is, observing the application, and it is figuring out how the application behaves and can therefore compile better, right? But this argument actually doesn't hold. It was true maybe for our first few releases. But we added by now very good profile guided optimizations, where you can gather a profile of your application and then use that profile to optimize it. And that's actually even better than what the JIT compiler does, because this way you can actually determine on what profile your application should be optimized on. The JIT compilers in all modern virtual machines, be it V8, be it Hotspot or JavaScript core from Apple, they all work in the same way, that they are observing the application's behavior at the beginning, and then at some point you do the JIT compilation, and it is very rare they would ever go back from the JIT compilation to rebuild the application in case it still behaves differently. That's a very rare occurrence. In many scenarios, it would just use the behavior at the beginning to determine the behavior at the end predict the behavior at the end of the application. And that's actually, first of all, that prediction is actually wrong for a lot of applications, because a lot of applications at the beginning are doing something else than they do on the long run. And this has actually very negative performance effects on some applications, because you get the profile pollution, it's called, from behavior at the beginning of the application. And this influences then the behavior and the performance of the application in the long run. It also makes the whole performance very unpredictable. There's many research papers on this as well, which are very funny, that showcase applications. It's the same application, you run it twice, and the peak performance is completely different, because it depends on unpredictable behavior at the beginning of the application. So all of these are actually downsides, and the final downside of this approach in general is that the JIT compilers, they are trying to optimize for the common case, because their overall goal is to make the program in common, on average, run faster. But this means that if they hit an uncommon case, they actually might run specifically slow. And for a lot of applications, that's actually not what you want. Like in my IntelliJ IDE, right? If I click on a new button somewhere that I didn't click before, I do not want suddenly my program to stall. And I want the button to be already fast, because it's a common button maybe that is clicked, right? But maybe it's not clicked at the beginning of the app, but later, right? So this is why an approach where the IntelliJ developers are determining based on a profile workload how the IDE should run, and it runs predictably fast on those workloads, is actually preferable. And this is why nowadays the peak performance on native image it's in many scenarios even better, because we have some advantages because of the closed type world. and we do not have disadvantages anymore from missing profiles.
Is there something where you still think JIT shines, or you would recommend to people as an approach?
I would recommend JIT only if you absolutely have to use it.
Right, okay.
Now, what are scenarios where you have to use it absolutely, right? You have to use it absolutely if you do not know your target platform, right? Because with AOT, you are fixing the machine code to an ARM device or to an x86 device. And sometimes you even want to fix yourself to certain hardware features of that device, right? So I want to use the newest AVX 512 on x86, right? So if you do not know your target hardware, then, well, the cheating, the ahead of time compilation might not be valid at all, or it might produce you binaries that are not as good. Now, thankfully, in a cloud environment, in most cases, you do know the target hardware because, I mean, hardware is less diverse nowadays in the cloud than it was, 30 years ago, and also you typically know where you deploy. So that would be one reason to use JIT, right? The other reason would be that you're running a program or language that is very hard to ahead of time compile because it's so dynamic. Mm-hmm. So we are still struggling for, let's say, JavaScript or Python, which are very dynamic languages, to provide the same level of ahead-of-time compilation capability that we have for JVM-based languages like Kotlin or Java. And so if your language doesn't allow you to ahead-of-time compile efficiently, that would be another reason. But otherwise, there is really the other downside, people saying, well, I need a build pipeline, right? But first of all, your build server, right, is much cheaper to operate, and then your production server, and so it's whatever cost you put into CPU cycles to ahead of time your compilation on the build server will be much more in the production server. Right? So I think those are the two only reasons to still use a JIT. So either you can't because you don't know the target platform, or you can't because your language is so dynamic.
Right.
But in general, it's just a predictable performance and so on, which is just better. And on the reflection restriction, one important aspect to that is that you're restricting reflection in our approach with native image because you need to configure what parts are reflectively accessible. But this restriction is also a security benefit because a lot of security exploits are based on arbitrary reflection, like the program deserializing like a message and calling out to something that it wasn't supposed to call out to. And these kind of breaches of security are not possible if you restrict and create include lists for your reflection access.
In terms of languages you just mentioned, which other languages again you currently kind of focus on also with Graal? And what are the use cases, by the way, that you see, common use cases, for, let's say, multi-languages in the same application?
So in terms of languages, our current focus, where we put the largest part of engineering efforts to make it better, is actually Python.
Okay.
So we think Python is a very, very interesting language, of course. You see it currently number one in a lot of programming language indices. And it's of course also the language of data science. And as our project focus is currently also on more geared towards creating further benefits for our Oracle database integrations, Python is currently definitely the number one thing we are working on. Now for Python, we have a standalone Python implementation that is an alternative to CPython. We call it GraalVM. And we are currently heavily investing in making this one better. We have certain properties where we are already better than CPython when we run Python. For example, on long-term peak performance, we are better because CPython is interpreted only, and GraalVM includes a JIT compiler. but we still also have regressions in other areas compared to C Python. And one of the things, by the way, that we learned also as we develop, maybe new exciting technologies sometimes is, yes, people like exciting new technology, but what they hate even more is if they have regressions.
Sure, yeah.
So this is actually sometimes very hard nowadays because things are very optimized. C Python is a very excellent implementation of Python that is very heavily optimized for low footprint and fast startup. And whatever implementation or whatever improvement we do over that, right? It's important that we do not regress on any metric in a way.
I was about to say, how do you make sure of that, by the way, or that you don't introduce some sort of, as you said, regressions, bugs, that it's always, at the same level? How do you make people maybe even believe it? Because at the end of the day, I think it's also about users believing this, I guess.
Yeah, I mean, on our end, we are doing a lot of testing and performance benchmarking with a huge regression tests, and every commit that goes into our repositories is tested against a very large set of programs. For Python specifically, we have challenges with compatibility because of this missing C extension support. There is the missing C extension interface. So Python does have C extensions, but they do not have a very clear defined interface. And this makes it very hard for us because C extensions sometimes depend on the internals of the Python runtime. And if we are having here an alternative runtime, we have to emulate all those internals. And Python C extensions, they can be really huge programs. Like if you look at TensorFlow or PyTorch, it's millions of lines of C++.
Right.
So in this sense, we do a lot of regression testing, and this way we try to avoid this, right? One of the projects we are currently doing, by the way, which is AI related, is we are for package compatibility. Some packages have good tests, which is great. But if a package does not have tests, we're currently using AI to generate tests. And this is a great use case because I don't care about the test itself because I have a reference implementation to check whether I only care, like the test itself can be a kind of some random exercise of that library. I only need to exercise some code paths there, and I compare the result against of the reference implementation against our implementation. Right. But yeah, it's very important for us to have zero regressions, and that's why so far we haven't. With GraalVM, we are still working on regressions on the warm-up and footprint side of things compared to C Python, but this will be the main focus at the moment. Right? We still have some focus on JavaScript as well. JavaScript is already one of these languages that are included in the Oracle database. Python is currently next up to be included in the Oracle database. And so in JavaScript, we continue developing. And then finally, we will also continue developing, however, of course, the GVM-based language support for us with a native image. But in this area, we are moving towards a system where native image will be able to run all programs because we add a Project Kramer, we call it, which is a Java interpreter to native image. And that can then run any program. And then the user can choose how much of the program he wants to ahead of time compile and how much of the program should be run dynamically. I mean, our recommendation, of course, is run everything ahead of time. But if that for some reason is not feasible for your application because it's maybe the application is dynamically generating a lot of code at runtime, which we think it's an anti-pattern, but there is applications out there that do that, then we will support them also in the context of native image.
Right. I just remember, by the way, that I think a couple of years ago, I was working on a tiny project which used ASCII Doctor written in Ruby, but there's also ASCII Doctor J. And then back in the day, I think I saw Graal and I thought, hey, could I somehow make it work that I could use GraalVM and then somehow plug the Ruby implementation of ASCII Doctor into it and run it. But I think back in the day, I never made it to work. Mm-hmm.
Yeah. But this the polyglot aspect, the really multilingual aspect, right? I think is something that is a unique property of our system. I think the way our polyglot story works, where you can run multiple languages in the same runtime, is quite unique in that the integration is extremely smooth. Meaning we have, when you run, for example, JavaScript in the context of a Kotlin application, you have the JavaScript objects and the Kotlin objects. You have them in the same heap. And you have them also the ability to, but they point at each other without any overhead whatsoever. And this is what allows us to really efficiently combine, because they will use the same garbage collector. Other approaches just sometimes they say, okay, why don't I embed V8 into my other virtual machine, right? So, but then you have like two virtual machines, they're competing for memory. You have like handles between them and so on. It becomes all very inefficient, and then you have the problem with cyclic garbage collection, because the two garbage collectors themselves are consistent. But what if there is like a cycle between those? You need an and so on. So in our approach of multi-language and polyglot, like the languages, they are sharing, they're running on the same heap, and they are allocated on the same heap. And our most popular embedding there so far was the JavaScript embedding. It's used by hundreds of open source projects, and also internally at some companies. So Amazon, for example, is now maintaining Graal JavaScript because they are using it embedded in one of their Java applications. And so this is a very popular use case for this embedding for us so far has been where you have a core platform that is written in a JVM-based language, but then you want to have a scripting capability on top of it. And this is what we provided with JavaScript. Now, lately, we moved a little bit more towards Python here as well, because as our Python implementation becomes more mature, we started this later than JavaScript, but the Python implementation is now more mature. And here, in addition to, well, enabling scripting in Python for your Java or Kotlin application, we can now also show that it's interesting to use a Python module, a Python wheel, in the context of a JVM-based application. And that's interesting because sometimes there's very interesting libraries written now in Python, and because of Python being the number one language at the moment, it is the case that the ecosystem in terms of utilities is the largest there. And now if you have an existing stack that is written in another language, like Kotlin here, then you would just use that. You just use that other library and you just embed it. And we are now at the point where this works relatively smooth. We also have integration into Maven and Gradle. So in your Maven POM file, you are specifying your Python dependencies, and it will, with a Maven plugin, they will just be pulled as well, right? And there's some people again that tell us, you guys are crazy. This is like, I would never do this, right? Yeah. But when you think about it for longer, it's not so crazy to actually. And the architecture is, yes, you have now one program that runs two languages, which sounds complex. But what's the alternative? The alternative is I start two programs. Mm-hmm. I have a socket connection between them. I have now to manage two heaps, and I need to have a communication between them, right? And we were talking to people at Red Hat, because Red Hat has like Dockling, which is one of these utilities that are very common nowadays to convert PDF to Markdown, or Excel files to Markdown and so on, right? And of course, it's available in Python. It's written in Python. But then I checked, okay, yeah, Quarkus, which is a Java-based framework, it has an extension for Dockling to call out to it. But when you look at what this extension does is it actually starts another process and a server communication which is like, yeah, this is not an efficient way to do it. It's a maintenance overhead and so on and so forth, right? And this is why we think that this Python embedding in JVM-based language is actually is very viable. And we're very happy that this is now catching on also with the frameworks. The Spring team was recently publishing that they are working on an extension to better support this. And because then you're not bound to a certain language ecosystem in this case, right?
Now that you have played with so many languages, not just play, but work with them actually, I have to ask you one question though. Do you have a favorite language? Do you have anything, favorite hobby language, favorite professional language, anything that kind of where you say, hey, this is so cool? You don't have to say Kotlin, by the way. This is not where I'm going.
I think Kotlin is a very cool language. Kotlin is a very cool language. I haven't written a lot of Kotlin, but I like that Kotlin is very concise and so on. I think Kotlin is a pretty cool language. I don't really have a big favorite. I have my first love as a language has been JavaScript.
Right.
Which some say, yeah, that explains a lot. But that's because it was my first language for when I was about 13 years old. I started learning JavaScript as my first language.
Right.
And the reason I learned it was because, well, here you could make cool buttons on a web browser, and I with all the negativity some people have about JavaScript, I like that it's the dynamic nature of it. I think, and that it's not bound to a very static type of object model, right? And I mean, we are ourselves always also a little bit, tempted. Maybe we should, we did the runtimes for a very long time. Maybe at some point we also should do a language, right? I mean, there's some say there's more programming languages than programs out there. Right. But why not add another one?
The Oracle language, right?
Yeah. Because I mean, one thing I like to say here in this area is that I mean, we as the GraalVM team, we actually now very much aligned and together with the Oracle database team because we feel that this is where we can make the most out of the Graal technologies. If we help further to also bridge the gap between data models and data management inside a database and in a programming language. I think that's still something that I feel like our industry is struggling with. Is that like, I have some data in a database, and then I have an object relational model, some ORM, sure. And then somewhere I go to some programming language, which then has a in-memory cache of the same thing, and the data types don't match and so on. So this is an area that from a research perspective is currently the most exciting for me at the moment. To see if we can somehow bridge that and say like, oh, I don't have such a semantics gap between how a database is storing and handling data and data types and how a programming language is storing and handling data types. And I mean, for communication in the web, right? So JSON is the most popular at the moment, where almost everybody is using JSON and REST APIs. But here again, some programming languages can work very well with JSON. That's why JavaScript is here very popular because it's natural. But other programming languages have a semantic mismatch with JSON, and then you always convert back and forth. So this constant marshalling and so on between data storage, data transportation layer, and the program itself. I think this is the most exciting thing that we can still, as an industry, kind of develop in a way that makes it much smoother, and with a much smaller gap between the different systems.
What do you think? And by the way, I fully agree. I mean, that would be great to have it solved as a problem. So let's see what's going to happen in the next decade. You already mentioned a tiny bit when you came to testing. What's your what do you think about AI and the role of AI in all of this, and maybe also your personal use of AI? I mean, do you use it much? I mean, to develop something, for example, to brainstorm something, yeah.
I do use AI, yes. I do not use it to write compiler optimizations. we were at some point asking AI, write me a read elimination phase for the Graal compiler, and because read elimination is a compiler term to optimize reads in a compiler graph and based on redundancies, right? And it would literally create me a compiler phase that deletes all reads from the program.
All right.
so that didn't work that well. So I'm not using it for developing core compiler things. I'm sometimes using it for creating test cases or exploring certain things. Like I, for example, used it to explore interpreter design, bytecode interpreter design, and different aspects of that. So I think while AI, I think it's definitely useful even right now. It's I think the fear that it's going to replace all the programmers in the near future is overrated. At least in the current way the technology works, it's not. I don't see that. And then I think the main aspect to make this better is to combine AI actually with compiler technologies, because I mean I can ask AI to refactor my code, or I can ask the IntelliJ IDE to refactor my code, right? Yeah. And the IntelliJ IDE I actually trust, because in 99.9% of the cases it will probably do the right thing.
It is very deterministic.
Yes. And the AI I would not necessarily trust, because it might do the right thing in 70% of the cases, right? And sometimes, I mean, as a compiler constructor, I was always, I mean, we're always transforming programs. We're always even generating programs and so on, right? And our premise when we do this transformation, we program those, it's always like, this has to be 100% correct. Mm-hmm. Like there's no...
Sure, there's...
And we get very strange bugs even on, because on a million times, maybe one time it might fail. And then even then it's I mean, when we compile a program, right, we're compiling like millions of methods. And so it's very important. It's 100% correct, right? And this 100% correctness is something that I miss on the AI approach when I would generate, or when I would let it like program something. But I think it might be possible in the future to somehow combine these technologies together to have like this. I mean, some of this is already happening, where you have like your MCP server, and your MCP server might have compiler knowledge, and then the AI is using it, right? Mm-hmm. Now in our project we are successfully using AI-based approaches already for quite some time. For example, for profile inference. I talked before how native image gets better from profiling, but the problem with profiling is people don't necessarily want to do the extra work to write the workload that is exercising the program to create the profile. And for this, we are now in native image. When you use the standard native image, you actually get an AI-based algorithm that is inferring the profile and is guessing the profile of a program. Right. And the nice thing about that as well, if the guess is wrong, it's not the end of the world. Your program runs a little bit slower in this one corner case, but it's not like it doesn't have to be that correct, right? And this already gives us, like, out of the box, I think it's like almost 10% improvements over the non-profiled version, by just making up the profiles. So this is one area where we have successfully applied this type of technologies, and it's shipping already in the last couple Graal releases. Now the generative AI aspect is something we are using currently to create test cases and to help with our compatibility with packages. Mm-hmm. So in these areas we are applying, and also within the team in a larger scale manner. Very interesting.
Then I want to change topics a tiny bit and get into the 1 billion row challenge.
Oh yes, that's my favorite.
It's something I've been working on. I did a couple of episodes I had to put on hold, unfortunately, now with Casey Moratori about it. To introduce you in terms of 1 billion row challenge, I think you are at the top of the leaderboard. I think you have the winning solution, so to say, if I'm not entirely mistaken. I would like to understand how you approach this whole thing, and just first of all, your general mindset going into it. I mean, yeah.
Yeah, the 1 million road challenge was a very fun exercise
Yeah.
on last year January, and it was interesting because out of the blue I come back from my winter vacation. I'm like I see on social media like Gunnar like go out with this thing and suddenly create a lot of excitement about this challenge for Java, and I looked at it, and the reason, of course, why I was very interested in it because I saw, that's a performance challenge with Java, and the Graal. I knew that the Graal JIT compiler is a very, very strong, the strongest, the fastest JIT compiler for Java. And so I thought, okay, I mean, obviously, if you use the Graal JIT, it should give you an advantage on this type of challenge. And this was got me interested in the challenge it's a showcase also for the runtime technology and our general vision to make programs run faster. And so I was, and I also found it very interesting how the challenge was it was a little bit of a cooperative challenge, right? It was like people are pushing ideas and then they're copying ideas from others and so on. And this is also, I mean, my solution has like 2 co-authors on them because I was taking ideas from their solutions that were so substantial that I couldn't claim it as my own.
Right.
So this kind of cooperative idea to together make something fast in the community and learn from each other was also something that I found very exciting and refreshing about the challenge. And so I was it was really cool. And Roy, who was very active and there as well. I gave a talk with him about the challenge at Devox, and so that was very, very cool community there.
How much time did you spend on solving that challenge? Actually, I mean, just roughly.
Yeah, I would say I was like thankfully it was time boxed to 1 month, right? and I think at the beginning of the month I was spending, maybe mostly on the weekend, maybe 10 hours each, which would be 20 hours. And then in the last week, maybe I guess more. So I think it's probably between 50 and 100 hours,
right?
Something like that.
Yeah.
So it was substantial. It was a substantial amount of effort that I spent on it, but it was very educational for me. I have to say. I mean, it wasn't. It was not definitely not. It was a time where I learned a lot about also our technology because I tried to apply it and I found I was finding bugs in our system while I was doing it. So because people are like, oh yeah, you're managing this team and it's supposed to do also something else. Well, I actually gave some bugs to the team at the same time. And also some feedback on this, right? And I learned something about performance and the performance architecture of Intel as well. Because
what did you learn?
So the main thing was around this branch prediction stuff, right? So in general in the challenge, right, it was the case that my solution was always like close to the leader, and it was starting to be the number one solution. And thankfully, almost all solutions in the top were starting to use the Graal compiler. Which was like for me already mission accomplished. So I'm like I don't need to win as long as the Graal JIT compiler is being used and comes out as the fastest JIT compiler for Java performance challenges. And I think that was for us, it was incredible marketing value to the extent that people thought that Gunnar was doing this on our behalf just from our paid from our marketing budget. Like no, you have nothing to do with that. It's just a lucky coincidence. Right. But yeah, but I was always top of the list, right? But and then on the last day, the deadline was at midnight, right? I thought my solution is perfect. It can never get better, and I thought like this is it. I just need to wait it out now until the deadline, and the solution will be the best, and I can't do anything anymore. And but then about 6 hours before the deadline, is like some other person was like submitting a new solution and was overtaking. And I'm like, damn it. That's like, like I spent so much time on this.
Right. And then 6 hours before.
I thought so hard that my solution cannot be better, right? And how can, and it wasn't overtaking by like a little bit, not just by like 2%, but it was overtaking by like 20%, I think, something like that.
Right.
So a big number. And I'm like, what happened here, right?
Yeah. What did happen?
Yeah, what did happen, right? So what did happen is that one thing in my solution, right? My solution was like relatively optimal from the number of instructions that are executing. It had the problem that it was mispredicting branches on every second row that is processed. So the way the challenge works is you need to go through all these rows, right? And a row could have, and the solution was specialized. My solution was specialized for when the row was only, or the name of the city on the row was only 8 characters, or when the name of the city of the row was 16 characters. So the solution was specializing on that. But because it was a random data set, it was this specialization code that was checking these 2 cases. It was always branch mispredicting on every second row. So while the solution in terms of number of instructions executed was fast, it had this branch mispredictions of the processor every second row. And I thought like, okay, it's a mass branch misprediction, but how bad can it be, right? But it actually turned out that this branch misprediction was absolutely terrible in the sense that it cost, I calculated back then later, I think it cost about 15 instructions. Mm-hmm. No, actually 15 cycles, which amounted to 50 instructions executed by the processor, because you have multiple instructions per cycle. Mm-hmm. So and I never thought this branch misprediction could be that bad. I knew branch predictions are bad, mispredictions are bad. You know that as a general knowledge, but I was never diving as deep into this topic that it would be so bad, right? And then I measured this again, and I'm like, oh no, I need to change the solution again. I need to make sure that I'm avoiding this branch misprediction. And it was possible to avoid that, but you had to do a lot of extra work. So you had to do a lot of extra work, like a lot of extra work on the processor. Meaning you were spending, and then we were spending like, I think 20 instructions extra, but avoiding this branch misprediction, and suddenly it was like smooth, right? And so I'm like, yeah, but it was like, it was
how much time was left before it got smooth? I mean, you said
I think it was only 2 hours left or less.
Right.
Yeah, it was like 2 hours before the deadline. I was like, but that was when my animal instincts kicked in. Like that. But I was like, yeah, like competitive, I was, because when when I was small, as a youth, I was doing a lot of programming competitions.
Right.
I was doing International Olympiad of Informatics.
Right.
And so I was very much in this like programming competition mindset back in the days. I was my best placing actually was the 3rd place worldwide in Wisconsin, California. So one time I was very successful as well there. So this kind of experience from back then was, for me, it was a little bit nostalgic almost, to like having this deadline. You have this deadline you need to submit until this time, and it needs to work now, right? And so this brought me back to my youth, more or less, and I got very competitive in the sports. so yeah, that was very fun. And
how would you people who are maybe not as deep as you are into this whole topic, how would you tell them to approach this challenge, just as an overall framework, kind of, when thinking about the performance, and how would you kind of teach people to tackle it?
Yeah, so I think the first thing that's important here is to and this is something I also learned in the programming competitions, is it's always best to, at least initially, go for a simple solution, even if you know it's not the optimal one. Because also when you program, and this again goes maybe a little bit back to the AI topic, is like when you program something that you're capable of programming, meaning it's not a too complex kind of algorithm, it's an algorithm that you can still feel and so on, you're actually very, very fast doing it. It costs you almost no time. But if you program something that's too complex and you make mistakes in it, and then you need to start searching those mistakes, this is when the real time sync comes. I learned this also when I was training and measuring my timings for the programming competitions. It was always the case that if I had an algorithm in my head that I understood fully and that I could just turn into code, it was very fast. But if I started to then have to debug the code because it was too hard for me, that's where the time was spent. And this is why also when we go back to the AI stuff, right? It's like it's great if the AI can generate me the code, but if I understand the problem, I can actually write it myself also very fast. And if I do not understand the program, now I'm left with a bunch of generated code that I can never debug, and I have to hope that somebody else does it for me, right? But so that's why in terms of people approaching such a challenge, I think it's important to first go for a simple solution, a solution that's straightforward, just does the right thing, and then you verify, okay, I have a solution. And only then you start optimizing your solution. Now, for optimizing your solution, it's also important that you first optimize the data structures and then you optimize the code. Because it's still the case, thanks to all this compiler technology and Intel hardware technology and so on, right, that your if statements or your micro optimizations on a certain if statement or loop or whatever, it can give you the last 5%, the last 10%. But the most important optimization first is to pick the right data structure and the right general algorithm, right? So, and this is also what we did in this challenge, is that first the data structures were picked and so on and so forth. And then only at the very end of it, then you start with the microarchitecture optimizations and so on. I mean, one very fun optimizations we did in the challenge was then we were interweaving the processing of the rows to make sure that there's more hardware instruction parallelism. but this kind of approaches, this kind of macro approaches, first of all, they only give you the last 5 to 10%, but also suddenly your solution is no longer readable, and you can no longer change anything anymore, right? So you start to go down a path where you sacrifice maintainability of the code for performance, right? And this is something you should do only at the very end. Yeah? And so for the 1 billion row challenge, I later afterwards I did the exercise. You can actually find it on my GitHub profile. I have a 1 billion row challenge repository where because afterwards I did the exercise to showcase exactly the versions that I was going through from version 1 to version 10.
Right.
So incrementally showcasing how I was developing this solution from version 1 to version 10. The thought process through it as well, yes. And it showcases the performance gain and the thought process of each solution. There's like a table on the bottom of this repository that showcases like which optimization or which change to the original version was gaining as much, right? And that was specifically also very interesting on this challenge, actually, to go through it so incrementally, right? Because this way you can also learn a little bit on what parts are so important and what are not, right? I mean, and we had then these issues where we were debugging the Linux kernel because the unmapping of the file was just taking over that much time and like. But it's also something I didn't, realize that much, and I learned, and I was a little bit about how these things can also happen, and how you profile them in the context of a GraalVM native image, for example.
It's crazy. It's just crazy how deep that tiny challenge actually can lead to, and how much time you can sink into it, and then just by the way, how fast was the final solution? I mean, the timing of that?
It depends, of course, on the type of machine. Right. So on my machine, it was 350 milliseconds.
Right.
So 350 milliseconds, but that was on an Intel i9, so in a relatively with 24 cores, and so there it was 350 milliseconds. And on the reference hardware, this was a not so strong machine, but it was, I think, about one, because it was also fixed on a certain number of cores. I think it was 8, I believe. It was 1.2 3 seconds or something.
Right.
But that's still extremely fast for this type of
Absolutely.
size of. It was a file with a gigabyte, right?
Yeah,
More
exactly.
than a
Yeah.
gigabyte.
I think it was the file was 13
13
gigabytes.
gigabyte, 13
yeah.
gigabyte file because it was exactly. It was 13 gigabyte file, and you process it on with Java here in a second, right?
Yeah.
And native image helped there again already because the solutions were getting so fast that the startup was also starting to be relevant. And other language communities also did some implementations, and some got even better, but they only got better by starting to write special assembly, like using vector instructions that are no longer portable and so on and so forth. If you would use standard C, for example, you couldn't get faster either if you don't do inline assembly.
By the way, because you mentioned it in kind of a side sentence, how did you train for your programming competitions?
I trained with algorithm books, of course. Sedgwick is one of the authors of the most famous ones there. And I trained then with this online. There's a couple online platforms. I wasn't using Topcoder. I was using USACO, which is a training platform from the American team, from the American IOI team. And I did the training, and there you learn everything about graph algorithms and so on, right? But then part of the training was for me also to measure myself and to measure how long do I take to understand a certain program. Like you get like a piece of paper. It has the problem. How long do you take to understand it? How long do I take to implement it? And how long do I take to debug it if something goes wrong?
Right, you timed all of that essentially.
Yeah, I timed all of that. Yeah, and I did a couple, test runs and so on, right? And from this, actually, I learned that the coding is the fastest part.
Right.
By far. Like you actually spend more time than you would think reading and understanding the program. So it's maybe like 10, 15 minutes. And then the coding for a simpler program would only be also 10, 15 minutes. But then if something goes wrong, you spend you can easily, the time flies by as you start debugging your program and trying to find an error. The time flies by so fast. And for me, this was not clear initially. For me, I always thought the main thing I'm doing is programming. So that's where I spend my time, right? And that was very interesting for me. And that later led me to change my strategy because I was my first contest was in South Korea, and I was 15, and I was programming. I was very ambitious, but I programmed 2 complex solutions that had small errors in them. And back in the days, it was also still the case that you submitted the program, and it would not give you a result back only once it's created.
Right.
So now they changed this now, which I think is not a very good change. I prefer that you submit the program and you have only one chance. You don't get a feedback as you submit it, right? So this is why my first participation I submitted a program, but it has a small error in it, and then I got very little points, right? And so then in my second attempt in this was in the US in Wisconsin for the IOI in 2000 and I think it was somewhere in the 2000s, and I changed my approach to go for maybe slightly simpler solutions, even write test programs for my solutions, because I knew all of this wouldn't cost me any time. Not I even wrote a test generator for my own program, but I knew that's 5 minutes, that's 10 minutes, and this was what made me then much more successful on this second attempt at the IOI in Wisconsin, and I think this is something that can also help. I'm trying to apply also now in our development, where. And that can help in the development of any complex software system. It's just this very important insight, and maybe you say that's obvious, but it's something people might kind of know it, or they would agree to it if you tell them it, but they actually not acting according to it,
Right,
right? This is why test-driven development and these kind of things they're good. They're popular and good, but actually they're extremely powerful because people I think subconsciously still underestimate how much time they spend debugging something and overestimate how much time they spend developing an algorithm or a program or a test generator or a verifier that they actually understand and they can develop quickly.
Mm-hmm. Just because you said you were 15 back then with the first competition, or maybe not the first, but at the time, how much time did you spend as a 15-year-old then? I mean, just prepping and doing all of this. Was that your main hobby, so to speak?
Yes,
Right.
that was my main hobby. I did also I did before the programming competition. I did like a competition with projects like home pages and so on, right? And it was my main hobby, and for me the school was always something that I'm like, I kind of need to get over with. But it was like that was not where I was mainly learning, but I was mainly learning in this area. Yeah.
Very interesting. Very interesting. All right. Then I like to end off these interviews with rapid fire questions. So before we come to rapid fire questions, I just remembered we're also referencing licenses, IntelliJ IDEA licenses. And as always, you'll have to answer a question from our guest and come relatively close to the actual answer. Do you have a question for the audience to kind of get into?
Yes. So my question for the audience is, like, the GraalVM project. It's a big open source project, and my team is maintaining and doing a lot of work on GitHub and open source. So my question for the audience is, how many lines of code, open source, of GraalVM and GraalVM related projects? So it's not only the main GraalVM repository, it's also, let's see, our JavaScript repository and our other languages. How many lines of code is maintained open source by the GraalVM team?
All right. Lines of code, GraalVM team. Let us know what you think. Put it down below in the comments. And then you'll be part of the license raffle, where we're going to announce the winners of the last 5 episodes or so in a couple of weeks, just around Christmas time. All right, then we'll come to the rapid fire round. What I usually do, as I already told you, I'll get the country that someone's from or works in, combine it with the topic, and ask ChatGPT, give me a couple of questions, combining these two. My mistake was, I now know you're from Austria, actually, but you live in Switzerland, Zurich. So we have some questions combining Zurich and GraalVM. So let's see what ChatGPT came up with. What is more complex, Swiss tax forms or escape analysis?
Swiss tax forms.
Swiss tax forms, right. Which is faster, Swiss watch or GraalVM's JIT warm-up?
GraalVM JIT warm-up.
GraalVM JIT warm-up, yeah, right. Then a very kind of, it's a very abstract question, which I wouldn't know how to answer, but maybe you do. If Zurich were a compiler optimization, which one would it be?
Read elimination.
Read elimination, okay.
Very efficient, very efficient.
Very efficient, okay.
Making things more efficient.
Okay.
Read elimination.
Okay. And if GraalVM were an alpine mountain, which one would it be? Now, I don't know how many alpine mountains you know by name, but... Matterhorn. All right. And what is more satisfying to you, a clean profiler trace or an alpine lake at sunrise?
Well, I like the lake, yes. I don't like profiler traces.
All right. And then the next question doesn't make too much sense anymore because you already answered. Maybe personally, what's a compiler feature you love that no one else basically loves?
Like my favorite compiler optimization is inlining. I think inlining is inlining and code duplication. So duplicating code. Right. Is the core of every compiler optimization. Yeah.
Right. All right. And then maybe just to wrap up, is there any place where people can learn more about, I don't know, anything you've just mentioned, or maybe even just for students who want to get into the whole topic of compilers, or people to learn more about GraalVM? Where could they go? Where would they go?
Yeah, absolutely. First, we have research papers. The most fun one is a research paper called OneVM to rule them all.
Right.
This explains this whole truffle language framework and partial evaluation related to it. So this is one. There's also a research paper on native image on our ahead of time compilation system, and then apart from the research papers, we do have a simple language repository that showcases how to build new languages on top of GraalVM, including tutorials. So that's something also for a student to, We actually, by the way, have, a shameless plug. We have, student internships at Graal. So if you're a student and you're as passionate about, compilers and programming languages as we are, please apply for our internships. We offer them in different locations around Europe and also the US. And for the 1 billion road challenge, as I mentioned, my GitHub profile, you will find the 1 billion road challenge repository. So if
by the way, if I'm not mistaken, it's not just a GitHub repo. I think did you also have a recorded video about it?
There is a DevOps deep dive. Yes, there's a DevOps deep dive that will help with understanding some of the details around that. And yes, you can potentially look at both the DevOps deep dive that I have with Roy. And the repository.
How long is that again? The deep dive?
It's 3 hours, I think. Yeah.
3 hours.
So you need to, you can you can split it up. That's the good thing on YouTube.
Right. So either it's going to be watch Lord of the Rings or the deep dive.
Yes,
so
exactly.
Right.
One of those. Yes, that's right. Yes.
All right. Well then, Thomas, thank you very much for being here and fascinating stuff. Thank you very much.
Thank you, Marcus. Thank you for having me here. Thanks everybody for listening.